Hi, this is Steve Kruin with Midland Technologies. It looks like we had quite a big, large attendance sign up here, but we're missing a few people yet. So we're going to go ahead and take about 3 minutes here to allow the rest of the attendees to sign in here. Thanks. Alrighty, everyone. Thank you so much for attending today. Once again, I am Steve Kruin, the National Sales Manager with Midland Technologies here in the Minneapolis-St. Paul metro area. Just a heads up before we get started, we're going to be doing things a little bit differently today due to the current COVID-19 situation. We do have one of our panelists working remotely to try and maintain that social distancing here. We are pleased to present this series of webinars Midland has developed. These webinars are focused on the high-pressure die casting industry. Midland, along with its sister companies, are all part of Innovance, a 100% employee-owned organization. As owners, we are all dedicated to providing our customers with the highest level of quality products and customer service. I would like to introduce the following presenters for this webinar. We have Larry Winkler, who is the president and owner of Wintech, Inc., Die Casting Consulting. In '96, Larry developed and implemented vacuum assistance in chill blocks and die casting, and a year later, working with Midland Technologies, commercialized the product. Larry has over 35 years in the die casting industry at 5 die casting companies in a variety of engineering roles. We also have Bill Zabracki. He is our engineering manager here at Midland, where he designs and coordinates all engineering activities. He has 30 plus years in the manufacturing industry, ranging from electromechanical circuit board test units, hydrostatic high-pressure valves and pump systems, and now high-pressure die casting components with an emphasis in designing, managing, operations, and quality control. If anyone has any questions, please submit your questions via the chat feature. Thank you again, and I will now hand it over to Bill Zabracki.
Hello, everyone. Thank you for joining us this morning. We're glad that you're able to attend. And we hope that everyone is well and safe during these times. Again, today we're going to be talking about reducing gas porosity and high pressure die casting. And some of the items that we'll be looking at is basically what is gas porosity and why do we have to reduce gas porosity. And then we'll look at the causes of gas porosity in both cold and hot chambers. We'll look at solutions for reducing porosity. And we'll be comparing those methods for reducing porosity as well. And also we'll be looking at design considerations. So what is gas porosity? Well, all of us in the high pressure die casting know about porosity. So everybody's experienced it. But with gas porosity, basically it's the internal porosity resulting from trapped gases in the molten metal during cavity fill. And so the following slides, we show a couple illustrations. And this first one, we have a closed cylinder with trapped air and into that cylinder. Now, with this particular cylinder does not have any vent to escape the air. So as the piston is moving forward, it's compressing that metal, and the molten metal will mix up with the air inside, and it will create porosity as the metal solidifies. And in the next slide, we show that same situation, but with a vent that's added. And again, as the piston is moving forward, it compresses the metal. The metal mixes up with the air that's trapped in that's being compressed in the cylinder as well. Some of that air escapes, but depending on the situation, you can still get air that mixes in and gives you gives you the porosity. And of course, that's all that we're trying to avoid. And with the next slide, I'll pass it on to Larry Winkler, and he can kind of go from there.
Good morning, everyone. Welcome to the presentation. As Bill indicated earlier, if you have any questions, just note those. We can address those at the end of the presentation. Being die casters, we all know why, have a pretty good idea and have different reasons why we need to reduce porosity in castings. And I think being the number one defect or the number one characterization of the high pressure die casting process, we know that porosity is one of the culprits. This is not to be confused with shrink porosity. We're not addressing shrink porosity in this particular presentation. So just to move forward here, why reduce porosity? Pretty obvious. The most likely characteristics, and we have these listed here. They're not the only reasons why you want to reduce. To improve the integrity of the casting, of course, give it strength. And then the most obvious, I guess, would be to improve surface appearance. You see this all the time in castings, blistered cold flow, knit lines, non-fill, and then outgassing. I'll talk a little bit about outgassing, but as we all know, castings outgas actually for the life of the part itself. So it's something that is inherent in castings. And then to improve the pressure tightness of the casting through leakage. We can have the next slide then. Now this is a cross-section area through not a real clear picture, but gives you the idea of a blister that's occurred in this particular casting. And of course, this blister was formed with air trapped in the metal, and as in this instance, as the casting cools, that air expands if the wall thickness doesn't have enough integrity to resist the air being compressed and expanding with the softer metal. Usually this will happen. I've seen it happen. You pull the casting out of the machine and that blister forms. You can watch it form right as it's laying on the conveyor. There are ways to prevent this, to minimize it. Obviously, the best one would be to eliminate the air. There's also some tricks you can use in the casting, and that process itself, and that would be quenching in water. That sometimes will prevent this. Next slide, please. Is another example of gas porosity, and you see this is one of the challenges, I think, for most casters until you become accustomed to viewing the two different styles of porosity, shrink porosity, and gas. This is a real good example of gas porosity. You'll note that the surface of the pore is usually fairly smooth. Not always, but generally speaking. And you can also get an idea of that porosity, not always, but in the location of the porosity itself within the casting. It's a good example of gas porosity trap. Next slide. This is an example of non-fill. And this is a rim of a casting. You can see that the metal has not solidified. A lot of times this is because of could be due to cold metal as a possibility, but again, it also could be attributed to the fact that that you don't have adequate evacuation of the cavity. Next slide. This is a cross section area cut through a casting that was drilled. You can kind of note the drilled hole that is sectioned through, moves through, and you can see the porosity right adjacent to that hole. Again, this casting leaked and was a problem. Again, example of porosity. Next slide. So the causes of gas porosity. The number one, it begins with the cold. If we just take the different components in the shot system and injection system, is air in the shot sleeve itself remaining there. The metal feed system, the runner, if it's not properly designed, the gating, and also location can be a contributor to gas porosity. The cavity detail itself, and of course, with the cavity detail, there's not much we can do with the detail that's in the cavity, just because that's one of the fixed items that we have. There's some things we can do with the design of the part that may help us reduce porosity, but as a general rule, we've got what we've got. And then the next contributor would be the residue, and that residue, of course, occurs when any residue that's left on the surface of the cavity or the runner or any part of the metal feed system comes in contact with the metals that's injected. So if our shot tip lube can be a contributor. Spray release agents remaining on surface, overspraying can be an issue. Water remaining on the cavity, and then the lack of adequate means of evacuation. Next slide. This is just a little schematic of a cross section of the shot sleeve, and of course to reduce porosity to air. Somehow we've got to get the air out of the metal feed system, and that evacuation begins when the plunger covers the pore hole in the case of vacuum. You can see by the okay, we'll move on. We'll go back. Just a note. Obviously, the green is the shot sleeve itself, runner, and then the cavity in red. Next slide. Okay, so we pour the metal, of course, in the sleeve, and we displace a certain amount of air that's in the sleeve. That normally is about 30%. Now, it can vary, obviously, by shot, but I would say in all my years of doing involved with die casting and looking at different percentages in the shot sleeve. If you're at 30% full, you're pretty good. Which means that the remaining 70% of the shot sleeve consists of air. Next slide. So this is just denoting the air portion, the metal, and where we've got air in the system itself prior to injection. Next slide. Okay, so the volume of air present in the sleeve, the runners, the gate, and the cavity, along with those gases formed, will end up somewhere in the casting during solidification if the cavity is not properly evacuated. Much of the air will be compressed, and we know that because of the nature of high pressure die casting. We can do some things to increase the pressure on the metal, and that's what we're referring to in this case. Trapped air will occur even if the slow shot speed is applied during slow shot phase. As a rule, if you use PQ square and you do some calculations, you'll determine and calculating the critical slow shot speed, you'll determine pretty quick that most machines, in particular the older machines, are not capable of achieving the recommended critical slow shot speed, which was intended when it was and the calculations were developed in the industry, was to minimize the amount of air. It's extremely difficult. You can sometimes gain, if you have a die casting machine with a parabolic shot end, you can help yourself somewhat to evacuate and help that less turbulent condition that we have with adding or mixing the air with the molten metal. But it is very difficult to achieve critical slow shot speed. Next slide. This illustration just indicates the plunger fully forward, and where we've illustrated the biscuit, the cavity, and the runner. Next slide. So causes of gas porosity in hot chamber. I don't know how many folks we have here with hot chamber machines. There are some tricks you can use to minimize the amount of gas. But air in a portion of the gooseneck can contribute. The metal feed system design, again, the runner, the gate location, the gate design, and the screw spreader itself, and of course the cavity detail. Next slide. So causes of gas porosity in the hot chamber: the residue generated during injection of the metal contribute in coming in contact with lubricants. Same thing as we have in the cold chamber. The spray, the water remaining on the surface, and again the lack of adequate evacuation. Next slide. This is just a cross-section area. But you can see that with the cross-section area, the problems that occur in the amount of air that is present prior to injecting the metal. You have to evacuate portion of the gooseneck, the nozzle, and the spreader, and of course the cavity. The next slide, please. The solution to evacuating air with the venting or vacuum. Time has to be considered when determining the area necessary to evacuate the cavity. Cavity fill time is critical, and knowing and predicting the cavity fill time. This time relates to the area that's necessary to evacuate the air and the gases. If you recall back in the earlier slides with the cylinder and the piston example, you can kind of visualize that the amount of time, there's a certain amount of time required for the air to escape. And if you haven't provided a means of the air escaping, it will end up obviously in in the casting. So from there, I'll turn it over to Bill.
Thank you, Larry. So there's two venting methods that are considered a push method. Two styles: conventional vents to atmosphere and vent blocks. And I think everyone is familiar with these types of styles. So the conventional vent, of course, is a small tract of a route that goes out into the outside of the die to vent out the gas. And the advantages of the conventional vents is that it does provide a passage for the air to be evacuated. It also provides a space for air to accumulate with the overflows. And it can be inexpensive to machine. But some of the disadvantages of the conventional vents is that they can tend to plug up. They're not very thick. They're only about 5 mils, 0.005 inches. They must be kept clean to function properly, and not enough area to allow evacuation during time available. So you do need quite a few vents to come out of your die, depending on the size of your of the mold that you're making, and sometimes that it doesn't allow you enough time to evacuate the area, depending on your real estate and such. So, and again, the thickness to the atmosphere is only 0.005, 0.006, so it's not very big. And they also they generate an excessive amount of scrap, resulting in lost metal to reclaim. So that's the first type of push method. The second style is using a vent block. And here the slide shows a couple of pictures of different size blocks that are available. Now with the vent block, the advantage is that you can vent through steel or a copper serrated block. It increases the area to evacuate compared to conventional venting. So the area of the block itself is can be about 10 times more than what you would get from one conventional vent track. So sometimes in certain cases the real estate needed to put a conventional block is less than to put in a vent block is less than using conventional venting. And you also can reclaim the metal lost compared to conventional vents from flash. So this is that can be a good reason why to go to a vent block in order to save your metal. And then also it provides a passage for the air to be evacuated like the conventional venting as well. The disadvantage of vent block, and again compared to the same as the conventional venting, is that it utilizes the push method of evacuating the air. So it's all reacting against as the metal's being pushed into the die, and it's being there isn't any additional source to help it pull that air out. So the other style of venting is with the vacuum method, and there's two styles for vacuum. And one of them is the valve style vacuum block. That utilizes a valve to stop the flow of metal and vacuum. So as you're pulling the vacuum through, pulling the air through, there will be some type of mechanism that will open the valve on a valve block. And those activation methods, there's either a timer or the metal position to close the valve, or it might be closing it by with the metal streaming through the die. Now this illustration shows a one with a vacuum block that with some type of device to open up to the and close the valve, and they're associated with OMC and Turner systems. Now the advantage of using a valve vacuum block that's using timers or a metal position for the control is that it does have a large area available for vacuum to flow. However, the disadvantages is that there is an initial cost associated with the pumps, the tanks, and controllers, and the installation as well. The valve blocks themselves are high in cost, and so are the replacement components. There's also high maintenance with the valve block, and of course that's the cost and of that with the downtime to clean those to maintain those blocks can be quite high. The time to pull vacuum is limited. The valve must close prior to the metal reaching the valve to prevent the valve from plugging. So there is a timing issue, and it can affect whether you're able to evacuate enough air out of your die. And also that these systems are typically a single unit, and they can't be used in a central vacuum system. So the other type of valve block is using the metal string to close the valve. And in this illustration, there's shown there's a plunger that shows that's in there that will be activated to close the valve. So a valve vacuum block using the metal string to close the valve. A couple of advantages. Again, there's a large area available for vacuum to flow, and it pulls the vacuum until the total shot is complete. Again, the disadvantage though is that the same as the other type of valve block is the initial cost for the pumps and tanks and such. Still high maintenance due to the plugging of the valves, and the high cost of the valve blocks themselves and their components. And then the molten metal is in contact with the activation valve each shot, and that can wear that component. And the same as the other one, that it cannot utilize a central vacuum system. So the next style of vacuum method is with a valveless vacuum block. And this slide shows a couple pictures of different sizes valveless vacuum blocks. Now there's some considerations with using the valveless style. There are no moving parts. There's low maintenance. You can use a central vacuum system. The control valve itself is within that outside of the block. The material used for the block is either steel or it could be beryllium-free copper. You can also have an insert, a copper insert that would go into a holder block of a H13 holder block. And so if you're more comfortable with using copper for your venting, for your vent blocks, you can with one's a style that has a holder, a steel holder block, you can replace the insert, the copper inserts during your PM. They're easy to install and retrofit to existing systems. So if you have a valve block in your machine now, in your die, you can easily replace that with a valveless vacuum block, depending on the situation, but it's easily retrofitting. Water cooling of the block is incorporated, and multiple blocks will provide the same area as a valve style. And you can save the material compared to conventional venting method as well, to save your metal. And the activation is from the start of the ejection to when the die opens. So you don't need to turn off your vacuum as soon as your shot is done. It basically you can keep the vacuum on until you open up the die. And again, I'll pass it on over to Larry with this slide.
Sure. This is two illustrations of castings that are heavily machined, and the grooves in both of these castings, the casting essentially as cast. We don't have a picture of the as cast, but this particular part, as you can see, has a series of grooves machined into it, rather deep. And this particular customer was experiencing higher rates of scrap. You'll note on the left side the porosity that existed after they machined the part. The sample on the right was after the application of vacuum. This is a pretty extreme, heavily machined casting that required vacuum to be successfully produced. Next slide. And successful evacuation depends on a number of things, and we take those into consideration, and you want to take them into consideration when you're dealing with methods of evacuation. The correct size of the outlets, the vents, or the vacuum themselves are critical. So that area, and going back to even the sizing of the block itself, is critical to the function. And as you can imagine, if you've done any calculations in gating and so forth, that you have to take into consideration not only the casting itself, but also the capabilities of the machine and the process that you've selected to produce the part. Along with that, we have the proper location of the outlets. Those are located at the last places to fill in the casting. And then the exact design of the outlet gates and runners are critical. That's both in the sizing and the configuration. Next slide. So the big thing for the die caster and consideration is what constitutes or what would require me to, obviously we have to evacuate the cavity. We know right away that any lack of evacuation, a method of evacuation, will cause gas porosity. So to minimize that, and we have to look at the casting and make an evaluation when we first get the job to determine whether or not we apply venting. We can use vent, or we need to apply vacuum assistance. So determining the volume and the time available to evacuate the cavity is critical. Determining the size of the vent and the vacuum block, obviously that's pretty critical. And there's a difference between the two areas. To establish the last place to fill, as I mentioned earlier, and that can be accomplished in a number of methods. The best method, of course, is to use some type of a simulation program to assist you in establishing that location. Locate outlets in the areas last to fill, as I mentioned. Group the outlets in pairs. This is critical. Now, there are certainly designs, and there's always exceptions to every rule. But if you can bring them out of the casting in pairs, it helps. And to extend the outlet runners away from the cavity to prevent backfilling. I know a lot of die casters like to tie all their overflows together, and this is from absolute. I've done it intentionally. I've tied two overflows together, and in most instances, I end up pushing metal back into the casting. Subsequently, I've introduced air back into the casting and just moved from one to the other. Again, not always. So I encourage people not to necessarily tie those in. It's very convenient to capture the overflows and scrap material. but is also detrimental to the ability of the evacuation system to function properly. Next slide. Okay, so the next, once we've decided that we're going to go with vacuum, one of the critical areas, or vent blocks for that matter, is to align and ensure ourselves that the two halves of the die are in alignment. And you'll note that if you've dealt with Midland block, there are keys built into the blocks, both vent and vacuum, that align it. It's critical if you were to retrofit that these be and the two halves be aligned properly. In the case of vacuum, of course, you want to shut off the atmosphere. In other words, you don't want to draw air into the cavity. Subsequently, the blocks themselves are preloaded and or seals. I personally have never used a seal in a die, primarily because they are a maintenance item. I know they're used, and I've seen designs with seals. If you have an application that requires sealing and you need a high degree of vacuum, good idea, use them. But in most instances, I have not seen a need for those. Activate the vacuum after you cover the floor hole, and of course it's critical. And then turn the vacuum off prior to opening the die. And controlling them or activating them can be many different methods. PLCs, computers, or limit switches. Even limit switches work fine to activate the on and off of the vacuum. And next slide, Bill.
Okay. So anyway, the summary of what we kind of talked about. So the evacuation with venture and vacuum is the key to reducing gas porosity. We have found that that helps in a considerably amount in the industry with different applications. You want to consider what method best fits your application, and you also want to consider what your customer expectations and requirements are. And in some cases, a certain amount of porosity might be acceptable for the particular parts you're making. So all those things you need to consider. And some of the services that are available in the industry include complete calculations to determine the size of the vacuum or vent blocks. And this is critical. You certainly don't want to put in a vent block that is too small, and so you want to make sure that you have the right size block. Determine the right evacuation area using the PQ square formula, and of course you can have multiple small blocks to get the area that you need. And so there's a lot of different options that you can do to make it work for your application. Complete design assistance of outlet runners, that's also available. And so if that's an assistance that's something you may need. Of course, with that, you want to know as Larry indicated, the flow simulation, so you can determine the last fill area of the die. And complete turnkey central or portable vacuum systems, including the pump, the reservoir, activation control valve, filter, hose, gauge, and accessories. That's all available in the industry as well. And also another consideration service is the vacuum alert system to monitor the vacuum level. And here at Midland, we happen to have a new system that we're developing called Vac Alert. And this is also a vacuum monitoring system. And it's a hardware software system with transducers to monitor the vacuum system. It can detect the vacuum level in the die cavity in real time. So that's a key too, to knowing how much vacuum are you pulling in your die, and then also to know how much vacuum you're pulling at the different filters and at the vent blocks themselves, the vacuum blocks themselves. It monitors key components and alerts before maintenance is needed. So in this particular system that we're developing, it'll give you it can send out a signal, or it can show it on the graph that you have a certain vacuum level, and if it's getting to a point if anybody that's familiar with vacuum it does require some preventive maintenance in the blocks or in the filters and such, and this vacuum system monitoring system will indicate when that's going to be needed, and it alerts the operator when the vacuum is too low. So that's the whole point of the system, is to give you a real-time indication of when your vacuum levels. And this slide here shows you a snapshot of our dashboard on the system, as you see in the upper right, and then also a graph that indicates as vacuum is being turned on. So on that graph, as you see the red line on the bottom, that's the sensor is monitoring the vacuum level right at the pump, and typically you have about 25 inches of mercury that you're pulling. And as the vacuum is turned on, as the valve is turned on to go through the rest of the system, through your filters and into your die, then you can see the lines come down and line up with the vacuum level at the pump level. And also the purple color is indicating that it perhaps is showing where the level is at the vacuum blocks or within the die, and it reacts very fast, and the curve there, the distance that you see, the little gap between the graphs, is just indicating that it's monitoring the vacuum level further down into the die. So it takes a millisecond or so to reach down to the level of the vacuum pump. Well, this is a system that we're developing that can help with your application too, to make sure that you're having proper vacuum levels. So with that concludes our presentation. And if you have any questions and such, you can go ahead and submit them, and Larry and I can kind of go through those and answer those questions for you.
Yeah, we have a few questions here. The first question, is there a correlation between the effort to reduce gas observed? It's worded a little funky here. Yeah, maybe break that down a little bit.
Can you move the cursor over to? Is that the full?
Oh, so here we go. That's, you know what? I'm sorry, guys. So, did the correlation between effort to reduce gas porosity and cycle time and shot weight observed?
Well, Larry, I think you agree too. So that determining your venting size and such, the shot weight and the cycle time is taken consideration in order to properly size your venting, and that of course will get you the proper size so that you will get the full benefits of evacuating the air to reduce that gas porosity.
Right. One of the things that we did early on, way back when this was developed, was to look at whether or not it is a cycle. What we use for timing is cavity fill time. And of course, cavity fill time is much shorter than the cycle, the entire cycle. And the reason that was selected is it provides really a safety factor. it's the same with the volumes. We not only include the volume of the entire shot, that would be the shot sleeve, runner, and cavity, and the overflows, but we also take into consideration the entire volume from the pore hole through to the valve. So at that point, we turn the vacuum on and off. So we've got plenty of safety factor built in the calculations, but we use our calculations, we use cavity fill time.
Right. Good.
Hope that answers.
Perfect. So the next question that we have here is how to eliminate air gas entrapment during slow shot. First phase in the cold chamber die casting for aluminum alloys.
Okay. Well, something that we touched a little bit about, and again, I think it was with that speed of the slow shot. And Larry, do you have more you can add on to that?
Sure. The only thing that, as I mentioned, because of the percentage of air being so great in the sleeve, that although it's certainly something to try to achieve, but in most instances, unless you make some effort in the design of your runner, and even in the sleeve, the telescope, I call it a telescope sleeve, to reduce the volume of air in there, and then you possibly could get a percentage high enough. The calculations for a critical slow shot speed, I believe, are above 45% full metal, and there aren't many jobs that I've seen that are in that area. So subsequently, yes, you can help yourself. As I mentioned, a parabolic shot end on a machine can reduce some of that also. It can help. But I hope that answers the question. Some people will move the plunger forward and dwell for a few percentages of a second until they evacuate the air in the sleeve, and then move forward to slow shot and subsequent. But again, that slows down your cycle. So everybody's looking for faster cycle times to reduce, to make parts quicker. That's a trade-off, and you have to really experiment with your particular machine to try to achieve that. Hope that helps.
Great, thanks, Larry. So another question that we've received here is, does too much dye spray cause porosity?
Absolutely.
Yeah. Yeah. So I think we can. Yeah. We kind of hit.
That's the short answer. Yeah, absolutely.
It does everything. I'm sorry. Go ahead, Larry. All right.
No, I well, it does.
I'm sorry.
It also has other detrimental effects, but yes, it can contribute for sure, because we create steam. If that's one of the critical things that we need to do, is make sure if you are running either a block or vacuum, and when I say a block, I mean a chill block, a vent block or a vacuum, is to make sure that you've properly sprayed and removed the as much residue or water off of your cavity, which you would do naturally, and off the block. Make sure you blow the block clean and get the residue off of it also. That can have a detrimental effect. Obviously, excessive dye spray will definitely leave a film on the die, and of course, when you inject the metal comes in contact with that residue and forms carbon, and that creates gas, which goes on and on and on.
Yeah, so you create more gas if when the metal hits that lubricant, and then now you have even more air or gas that you need to pull out and get it mixed up in there.
Very good.
And I think the key too is if to blow it off. Try to do as much as you can to blow off that lubricant after you apply it.
Absolutely.
Yeah, so we've got an interesting question here. One of the attendees is asking, how much casting pressure is required to break up porosity into micro porosity? Is that something that can be achieved by, increasing casting pressure?
It certainly doesn't hurt. Again, that's a balance, and when you're in the design stage, I don't have a number. I couldn't give you a number for that because I've never done the experiments to arrive at how you would eliminate or to come up with that number. But I do know that impact pressure, we all know that, on the metal is an advantage of the process itself, so that we can achieve, let's say, the minimization of the size of the pores. Okay, that's the reason why NADCA and, well, beyond NADCA prior to that, but I believe there were studies done that indicated that you want to have a minimum impact pressure of 3,000 psi on your metal. Higher than that is good to a point, okay? And that point would be at that point where you've exceeded the locking tonnage of the machine. That has to do with how you set the machine and what diameter tips you're using, shot sleeve, and so forth, and what kind of accumulator pressure you're running on the machine. So, but to answer the question straight away, no, I don't know what the pressure is in the casting. I know that impact pressure is 3,000 psi minimum.
Perfect. So the last few questions we have here are actually kind of good summary points here. I know we've touched on them quite a bit during the presentation, but a great way to round out this webinar here. We have, is vacuum technology beneficial and economical in reducing porosity? And the last question is, what is the best way to stop gas porosity in high pressure die casting? Just want to maybe give a little bit of a final summary here for everybody.
Sure. Good question, Joe. Certainly the beneficial, the benefit of using vacuum is we've seen quite a number of results, good results with this. Recently we experienced where a company had about 10 to 12% scrap rate, and they started utilizing vacuum with the valveless blocks, and they're down to like 1 to 2%. It was quite exceptional, and you think about it, with vacuum, you have an extra source that's helping you pull that gas out, and that's you're not just relying on the metal pushing the gas out. So it's giving you that benefit to extract the gas as much as you can. And Larry, have you got more to
I just wanted to mention, I think, was the last portion of that question about the elimination of porosity. That's impossible.
Correct. Yes.
Yeah. There is no way to eliminate porosity. It is inherent in this process, in high pressure die cast. I don't know of any casting that is porosity free. So to answer that, no, you can't eliminate it, but you can reduce it. Always the question has been with die casters has been, what size is the porosity? Where is the porosity? Okay, and what can I do to either move it and to minimize it? And with vacuum, we minimize porosity. That's really the bottom line. Right.
Yeah, and then like we mentioned, both proper venting size and the gated runner design, that all those take into consideration as well. But you won't be able to eliminate it completely, but you'll certainly be able to reduce it.
Correct.
Good.
And by the way, just a quick mention here. Yes, you can. And no one asked the question: can I over evacuate my cavity? And yes, you can. And that would be the same thing as backing off the lock on a machine to let the die breathe. Okay, we used to call it let the die breathe, and you back the lock off and or put shims in the tool and shim the die open and make shots. Well, what you're doing then is you're reducing the amount of pressure on the metal, which subsequently ends up with internal porosity. You get a nice looking casting on the exterior, but a poor casting on the interior. And I think if you've been in die casting, you know that. But just to pass that note along, yeah, you can over evacuate. That's the reason we run calculations, determine proper sizes and so forth.
Right. Yeah, you do want to have a decent amount of resistance in order to evacuate it properly. And if correct me if I'm wrong there, Blair, but if you have too much evacuation area, that's the that can like you said, kind of you get maybe a smoother surface, or the surface looks okay, but inside you're going to create more porosity.
Correct. Internal porosity. Correct.
Okay.
Perfect. Let's take one more look here, and it looks like that is the last of the questions that we have. I want to quickly thank everybody for submitting your questions here. Bill, I think you've got a little bit left to say there.
So next month our next webinar will be the introduction to Valveless, Midland's new vacuum monitoring system that we just talked about, and you can go online on our website to register for that webinar. It's May 19th at 10 a.m. And also you can follow us on LinkedIn as well, and we will by doing that you'll receive updates about upcoming events and all things happening at Midland Technologies. So I want to thank everyone for joining us today, and I think we also have a copy of today's webinar available too.
Yeah, correct, Bill. Here, if you go under our handouts here, we do have a PDF file that'll go through the webinar that we covered today.
So, on behalf of myself and the rest of us at Midland here, thank you again for your participation. Larry, any final words?
No, that's it. Just stay healthy.
Indeed, yes. Good point.
And join us next.
Right.
Thank you.
Thank you then.